Okay, continuing with our discussion of vectors and planes, this is part 2. So the question comes up, where do these equations of planes come from? How do we know that ax plus by plus cz equals d is a plane, and how did we come up with that? So here's how it looks. If we take any point in the plane, so this parallelogram is supposed to be a plane, kind of like a magic carpet that goes forever. Now imagine that this is a point in the plane A, and then we look at a vector that is perpendicular to the plane itself, and I'm going to call that n. So if a vector an, so we're going to call that vector an, is perpendicular to a plane, then it is perpendicular to all of the vectors in the plane. Then it is perpendicular to all of the vectors in the plane. That kind of takes a moment, I think, to digest. But remember, that vector is movable, so we can slide that around, and any plane that you draw that is completely contained in that, any vector that you draw that's completely contained in that plane is going to be perpendicular to the vector an. So if P is any point in the plane, if P is any point in the plane, then it must be true that vector an is going to be perpendicular to vector AP. And if two vectors are perpendicular, that means that their dot products are going to equal 0. So vector an dotted with vector AP must be equal to 0. This is going to be key. So this right there that I put the box around is a vector equation of the plane. And so we're going to see how do we go from the vector equation to what we're looking for here, this ax plus by plus cz equals d. So let's see what kind of, let's see what kind of Cartesian equation this leads to. What kind of Cartesian equation this leads to. So let's pick, we're going to call A, that point that we have up in our picture there. So we're going to call A, its coordinates are going to be x sub 0, y sub 0, comma, z sub 0. So there's that initial point on our perpendicular vector, sometimes called a normal vector. So this is now going to be fixed. So A, we're going to say, is fixed. We're not choosing it to be anything at all. And it's not going to move around. And then we're going to pick the point P to be, we're going to say P has coordinates x, y, and z, and P is kind of our generic point. So it is any point in the plane, any point or every point in the plane. So just to visualize it, I'm going to pick P to be over here, and I'm going to label it x, y, z. So there is our point P. And then we know that the vector AP, so vector AP, we know is going to be this tip minus tail. So it's going to be x minus x sub 0, so I'm taking the x coordinate of the P minus the x sub 0 of the A, and y minus y sub 0, and z minus z sub 0. So there is our vector AP. And let's just call vector AN. I think I made that yellow. So I'm going to go AN. Just to make things simple, I'm going to call it's going to be ABC. Those are its components. So it'll be nice and clean. So that's our is a vector, we'll say perpendicular to the plane. So that's its defining characteristic there. So what we know then is that AN, our normal vector or vector perpendicular to the plane, dotted with AP, must be equal to 0. That's what it means. So you can kind of see that if, there's our vector AP and there's our vector AN, no matter where we put P in the plane, it's going to be true that AN dotted with AP is going to be 0. So what that means, let's see, if we take the dot product, we're going to get x minus x sub 0 times A plus B times y minus y sub 0 plus C times Z minus Z sub 0 must be equal to 0. That's what it means for two vectors to be perpendiculars. Their dot product is going to be 0. Well, if we distribute that, we're going to get AX minus AX sub 0 plus BY minus BY sub 0 plus CZ minus CZ sub 0 equals 0. So if we leave the stuff without the minus signs on the left side, we have the AX plus BY plus CZ, and we add those others to the other side, we get AX sub 0 plus BY sub 0 plus CZ sub 0. So this is exactly what we said when our equation of a plane is AX plus BY plus CZ equals D. So remember, these are just going to be numbers here, and now we even know how to come up with that D. The D is actually going to be that A times X sub 0 plus B times Y sub 0 plus C times Z sub 0, where the ABC are coming from our normal vector that we saw over here, and the X sub 0, Y sub 0, Z sub 0 is coming from our point A, that is the base of the initial point of that normal vector. Okay, well this is actually a formula here for coming up with an equation of a plane. So let's look at an example and see what this is going to look like with actual numbers in it. So let's say that our vector perpendicular to the plane, is going to be, we'll call it V, and it's going to be 2, negative 1, 3. And our point A, which is just any, it's going to be the base of that. So A is going to be, A is our point that is on the plane. So that's like our kind of that random XYZ, except it's not the random one, it's just any point that's in the plane. And so A, we're going to say is 4, 3, negative 2 is any point in the plane. So with that, what we can do is we know from our normal vector here, this is going to be our A, B, and C. And we know that the D that we're looking for, this D is going to come from our the 2 from the A times the 4 in that point A, plus negative 1 from our normal vector times 3, which is that y-coordinate of that point in the plane, and then plus 3 times, and then we have a negative 2 is that z-coordinate of that point in the plane. And so that's going to be, it looks like 8 minus 3 minus 6, so that's going to be a negative 1. So that is our value of D. And so that means our equation of the plane is going to be, we're picking out the A, B, and C from our normal vector, that vector V. So it's going to be 2x minus y plus 3z equal to D the negative 1. That's the equation of the plane with normal vector V, that is vector perpendicular to the plane, and the plane that contains this point. Okay, I'm going to go to a new screen here. So our first example is we're going to be given 2 points and try to find a Cartesian equation. That's something in the form ax plus by plus cz equals d for a plane perpendicular to the vector AB at its midpoint. So in our diagram down below here, you can see our vector AB with its midpoint drawn on there, and we've drawn that blue plane that's supposed to be perpendicular to that vector. So to figure this out, we're going to need vector AB, and vector AB is going to be tip minus tail. So we'll go 3 minus the 1, negative 4 minus 0, and 6 minus 2. So that's going to be 2, negative 4, and 4. Now the midpoint of that vector AB is going to be the average of the x and y and z coordinates of AB. So that midpoint, I'm going to do parentheses, is going to be 1 plus 3 divided by 2, 0 and minus 4 divided by 2, and 2 plus 6 divided by 2. So that midpoint is going to be 2, negative 4 divided by 2 is negative 2, and 8 divided by 2 is 4. So we have our vector and our point. So then we're ready to come up with the equation of the plane, which is going to be ax plus by plus cz equal to d. Now the normal vector to the plane, our ABC, is going to be a vector perpendicular to the plane, but we can see in the picture that's exactly vector AB. So we can use as our normal vector 2, negative 4, 4. And we'll need a point that's on the plane, and so our point is going to be our midpoint. So we're going to get the 2 is our A times the x-coordinate of the point 2, and then our B is going to be the negative 4, which is the y component of our normal vector, and times the negative 2, that's the y-coordinate of the point on our plane, and then plus the 4, which comes from our normal vector, times the 4, that is the z component of z-coordinate of our midpoint, and that's going to be, excuse me, that's going to be d. So that's going to be 4 plus 8 plus 16 is going to be our d. That looks like 28. So our plane is going to be 2x minus 4y plus 4z. That's coming from our normal vector, equal to 28. Or alternatively, we could divide everything by 2 and make it look maybe a little nicer. X minus 2y plus 2z equals 14. Those are equivalent to each other. That's going to be the equation of our plane. Let's look at another kind of example. Can we find an equation of the plane tangent to the sphere, x minus 7 squared plus y minus 5 squared plus z plus 1 squared equals 121 at that point P? So you can imagine we've got some sphere, and then we're going to take some plane that's going to intersect that sphere in a single point. And so we can see that we can get our center is going to be 7, 5, negative 1. That's that point. So since we're given the point P here, our vector CP is going to be tip minus tail, so negative 2 minus 7, 4 minus the 5, and 1 minus the negative 1. So that is going to be the vector negative 9, 4. That's a 4 minus 5 is negative 1. Can't read my own writing. And then a 2. So there is our radius, our vector CP. Now we know that a radius drawn to a sphere is perpendicular. So this is going to be our normal vector to the plane, and the point on the plane is going to be our P. And so we're going to go A is the negative 9, that's coming from our normal vector, times the negative 2, which is the x component of our point, and then minus 1, and times the negative 1, and then plus 2 times the 1 will give us our d. So that's going to be 18 plus 2 plus 2, so that looks like 22 for the d. So we have negative 9x, this is our normal vector, minus y plus 2z is equal to 22. And that's the equation of that plane that is tangent to the sphere. Kind of cool? So if u and v are perpendicular to planes p and q respectively, what must be true if p and q are perpendicular? So if we have our normal vectors u and v, which you can see in the yellow and the red, and I've tried to draw as best I can here two perpendicular planes, and if you look at those vectors and their extensions, you can see that if the planes are perpendicular, then u also must be perpendicular to v. So those normal vectors will also be perpendicular. What if the plane P and Q are parallel? Then I think you can see in the picture that the normal vectors u and v will also be parallel to each other. You can see in parentheses it works both ways. So if we know the planes are perpendicular, their normal vectors are also perpendicular. If we knew that the normal vectors were perpendicular, we could conclude the planes are perpendicular. Likewise, if the planes are parallel, so are the normal vectors. And if we knew the normal vectors were parallel, we could conclude the planes are parallel as well. We're going to show that these two planes are perpendicular to each other. So we can show that by showing their normal vectors are perpendicular. So the normal vector to this plane is going to be 12, let me try that again. It's going to be 12, negative 6, negative 3. And the normal vector to the second plane is going to be 1, 1, 2. So I'll call that v. So if we can show that u is perpendicular to v, then we can conclude that those planes are perpendicular. And we can check for the perpendicularity by taking their dot products. So if we take u dot v, that's 12 times 1 plus the negative 6 times 1 plus the negative 3 times 2. So that's going to be 12 minus 6 minus another 6, and that is indeed 0. And so then we know that they are perpendicular. Whoops. So let's look at our next example here. We're going to show that these two planes are parallel. So in much the same way, we'll look at our normal vector for the first plane, which is going to be 12, negative 6, negative 3, and our normal vector for the second plane, which is negative 8, 4, 2. To show parallel, we want those to be a multiple of each other. So we can say 12, the x component is some unknown constant k times negative 8. That's the x component in the second vector. And that tells us that if these really are going to be parallel, that our k is going to be a negative, let's see, divided by 4, that's going to be 3/2. So now we'll see if that works for the other components. So -6, is that question mark going to be 3/2 times 4, and in -3/2 times 4, and in fact that is true, so that works. And then the question is -3 equal to -3/2 times 2, and indeed it is. And so we have shown that those normal vectors are parallel, and therefore so are the planes. I'll just call them P and Q. All right, very good.